So we can do calculus with vector-valued functions. We could take limits, we could take derivatives, we can integrate. Let's do an example. So suppose I have the vector-valued function r, which is given by sine t 1 minus cosine t and t squared. Then let's just do a few calculations just to show you how it goes. First, let's do the limit as t goes to pi of my vector-valued function r of t. Now, what you're going to do is just take the limit of each component. So when we take limits or derivatives or integrals of vector-valued functions, all we're going to do is just operate on each component separately. So I'm going to take the limit as t goes to pi of sine t, that's 0. I'm going to take the limit as t goes to pi of 1 minus cosine t, that's 2, and then pi squared. That's it. So the message I'm trying to get across is that when you take limits, you just evaluate each limit component-wise. So take the 3 limits and put them in a vector. Derivatives are similar. So the derivative of the vector-valued function r will be the derivative of each component. So the derivative of sine is cosine. The derivative of this middle function is sine t. And the derivative of t squared is 2t. And I can also integrate. So I can integrate my vector-valued function. When you integrate, you get negative cosine t. I think you'll get t minus sine t and 1/3 t cubed. Now when you have an indefinite integral, you have a plus c. This time, we're actually going to get c1, c2, c3. One extra constant from each of the 3 terms. So sometimes instead of writing this vector form out, we'll just write plus a constant vector. Okay, so what does the derivative actually do for us in this situation? So geometrically, the derivative of your vector-valued function, r prime of x, is a vector that's in a direction that's tangent to the curve traced out by your vector-valued function. Let me draw you a picture of what I mean by that and tell you why it works. So I'm only going to draw my picture in R2. We've been doing vector-valued functions in R3, but if you just omit the 3rd component, you got a vector-valued function in R2. That's easier for me to draw. So I've got some vector-valued function. That means that here, for example, is the vector r of t. The vector points to different places on this curve, and as t changes, I trace out this path of some particle or something. Well, we know from calculus 1 that the derivative r prime of t is the limit as h goes to 0 of r of t plus h minus r of t, all divided by h. So here I have a vector r of t depicted in my picture. R of t plus h would be a vector that I get by increasing t by just a little bit. So if I increase the argument t a little bit, I'll get a vector maybe over here that is r of t plus h. So when I subtract these two vectors, I get a vector that starts in this place on the curve and ends over here. So this vector that I'm showing you in the picture at this location is the vector r of t plus h minus r of t. H is just a constant, so the direction of the vector is unaffected by dividing by h. It's just scaling the vector. So meaning that as I take the limit as h goes to 0, I'm going to get a vector that's perfectly tangent to my curve. So that's the geometric reason that the derivative of your vector valued function is given by, is a vector tangent to the curve. Let's end this video with an example. How about this? Let's find a unit vector tangent to the curve. Let's say r of t is the vector valued function 3 minus t, t squared, and log t at, let's say, t equals 2. So this describes some curve in three-dimensional space. At t equals 2, I have a point on that curve, and I'd like to know the tangent vector at that place, a unit tangent vector. So here's my answer. The derivative of our vector-valued function is easy to calculate. So the derivative of our vector-valued function is, let's see here, -1, 2t, 1 over t. At t equals 2, I get the vector -1, 4, 1/2. So that is a vector in the direction of the tangent vector, but it may not be a unit vector. So this is the correct direction, but maybe not the direct length. So the unit vector that I'm looking for is this vector divided by the length of that vector. So the length of that vector is 1 over the square root of 1 squared plus 4 squared plus 1/2 squared times the vector -1, 4, 1/2. Okay, we'll continue this discussion in our next video. I'll see you there.